My name is Spiros Kousouris. I'm a project manager for Suite 5, and I will be presenting the AI-based misbehavior detection engine developed in the context of Work Package 4. The motivation behind our engine comes from our aim on strengthening trust in embedded systems, while also identifying the crucial role of misbehavior detection systems. Such systems are essential in embedded systems, and especially in cooperative environments, and have gained attention for being able to identify anomalous behavior in transmitted messages. Misbehavior detection systems can combine various plausibility factors to ensure the consistency of devices' behavioral attributes, while being able to provide vital indicators of a device trustworthiness which extend beyond mere attestation attributes. Within REWIRE, we introduced the AI-based misbehavior detection engine, complementary to the attestation, which is designed to constantly monitor and identify flag potential threats from anomalous device behavior. It operates in an automated manner based on the reception of application data. Thus, it can proactively identify and guide the formulation of optimal mitigation strategies for risk in embedded system based on identifying events which are flagged as indicators of potential risk. Moreover, it offers security and resilience of cooperative environments while fortifying trust, preserving service graph chain integrity, and safeguarding against threats. In respect to its internal architecture, as you can see in the figure, the AI-based misbehavior detection engine is compiled by three main layers. On top, in orange color, we have the presentation layer, which essentially is the user interface that enables users, such as data scientists, data analysts, to design and execute data analytic pipelines, derive the analytical insights, and visualize the results. In blue color in the middle, we have the business logic layer, which is basically the back end of our engine, and comprises of the back-end level, which includes the analytics composer back-end, responsible for the processing of the data analytics tasks, and at execution level, we have the data manipulation, the analytics executor, and the result exposure. The last one is responsible for sending the values of risk indicators, i.e. the results of our analysis, to the risk assessment module of REWIRE. Finally, at the bottom, we have the data access data storage layer, which represents the key data entry point to our engine, and includes the data preprocessor, which is responsible for fetching and preprocessing the application data as these are extracted from the far-edge devices through REWIRE's blockchain infrastructure, and the data storage, which is responsible for the storage and retrieval of the data utilized within the engine. As core innovation points of our engine, we identify its flexible classification model. The engine has the ability to accommodate various types of ready-to-use classification model, as these shown here in these two columns in the bullets, which can be tailored to specific data characteristics and application domain requirements. In addition, our engine supports trustworthy AI within REWIRE, as it leverages the data veracity that's introduced by the secure oracles. It builds on a data-centric trust establishment based on security claims associated with the data. These are verified by the town crier, and operates on trustworthy data. Thus, it offers enhanced accuracy when detecting anomalies. The AI-based misbehavior detection engine will be demonstrated and evaluated in two use cases in the REWIRE project. The first one is the smart satellites use case, where the objective is to analyze the satellite's operational patterns and detect misbehaviors that could compromise their integrity in operation, and flag such behaviors so that the satellite operator can intervene. As you can see in this figure, we have already identified 4 baseline plausible checks. These are reported in deliverable D5.1. 3 of those are dealing with unsupervised anomaly detection, and more specifically on predicting satellite resets, on detecting pointing anomalies, and another one on detecting contextual anomalies in the satellite's telemetry data. The fourth one consists of an early warning system that will be utilizing rule-based method. The instantiation in the smart cities use case will be reported in the next reporting period. Now, for our demo, we're going to be looking at the utilization of the engine in the smart satellites use case. The focus of our analysis lies on leveraging the available data provided by the use case partner for the development of the algorithmic model. And the problem we are trying to solve, given the variables we have, is an imbalanced classification approach where we try to predict if the satellite will perform a reset based on its azimuth, elevation range, calendar information, and satellite name. We have to note that while a simple rule-based system will suffice for this analysis, The aim of the video is to showcase the engine's proof of concept and its user interface. A quick data asset description that is used in our analysis. The dataset consists of synthetic data from 5 satellites. Data variables are included are azimuth, elevation, range, and satellite time. These derive from 409 ground station, and the datasets consist of 125,000 rows. Now, going into our user interface of our engine, this is the main view where a data scientist can design and execute a data analytics pipeline. As you can see here, a data scientist has already designed a data pipeline, an analytics pipeline for our given problem of predicting satellite research. By zooming in, you can see the different blocks this pipeline is made. In blue color, we have the input blocks, such as read dataset, read the data frame, etc. These are typically at the very start of a pipeline. And then in green color, we have various what we call data preparation block. For each of these blocks, the data scientist has to configure the parameters of this function. And then moving on, in orange color, we have what we call the machine learning blocks. In this instance, we have the training of the model with one hot encoder, and here we have fit a transformer on the dataset. I'm moving on to the end of the pipeline. So you can see here at the very end, of the very last steps, firstly we have the training of the model with an XGBoost classifier, and then we have application of the model. And with further data preparation steps, we finally have the evaluation of the classification task. Here the user again has to configure the parameters of this function, and by going to the results view, sorry about that, let's go to the end again. So we were here on the classification task, and going to the table view, the user can see various evaluation metrics for this task, such as accuracy, F1 average binary, precision, and recall. Going back to our pipeline, at the very end, you have noticed also there's a purple block. These are what we call output blocks, so the results now can be stored and sent over to the risk assessment module of REWIRE. By clicking here, again the user has to configure some parameters, and going to the results view, selecting the given results, the user can configure how the results would look like, change the name, change the access title, the type of graph, etc. So running this and executing this pipeline, next step the user can see a visualization of the results. As you can see here, we have the visualization of predicting research for this given satellite with the name Skoltech, and with light green we have the actual research, and with dark green the predicted research. This can be also downloaded. These are like downloadable file, as we said, can be sent through APIs to the risk assessment module. So going back, future steps for our work, immediate next steps in the smart satellite use case. We have done a preliminary analysis and we have preliminary results, but we need to further investigate and fine-tune the classification model. Also execute the predefined baseline plausible check as a minimum, and then, as we have already started the evaluation, report it in D6.1. For the smart city use case, we will take similar steps, undertake a preliminary data analysis to extract the baseline plausibility checks, then undertake the actual analysis and identify the results, and then evaluate the engine for this use case, which again will be reported in D6.1. As long-term action, we have the thorough evaluation of the AI-based misbehavior detection engine, which will be reported in D6.2. Thank you very much for your time.